Here's a final example using the quantum mechanical harmonic oscillator. What is the expectation value of position for harmonic oscillator in the n equal 2 state? All right, so we want expectation value for position. Expectation value for position will be equal to, we're going to integrate over all in space, minus infinity to infinity. And again, let's say the n equal 2, so we'll just put a 2 down here. That will be the wave function corresponding to the n equal 2 complex conjugate times the operator corresponding to position times the wave function in state 2 and integrated over all space. Now we're going to use the harmonic oscillator. So this is equal to the integration minus infinity to plus infinity of, well, remember what the wave function was for harmonic oscillator? It was a bunch of constants times the Hermite polynomial for, and we're doing the n equal 2 state, so it'll be the second order Hermite polynomial, e to the minus, this would be alpha x squared over 2, those are constants, complex conjugate, times the position operator, which just multiply by x, times, again, those constants, the Hermite polynomial, e to the minus alpha x squared over 2. All right, so, and this was the Hermite polynomial for n equal 2. So let's take a look at the Hermite polynomials for n equal 2. Okay, so we go to the Wikipedia article. Here it is, Hermite polynomials. We wanted the n equal 2 Hermite polynomial. Here it is, n equal 2. Well, sorry, that's the mathematicians. Let's go down here, the physicist. Okay, here's the physicist polynomial, Hermite polynomial, n equal 2. It's 4x squared minus 2. All right, so we could put 4x squared minus 2 there, and then we could try to integrate this, and there's an x there, and so on. But let's use the fact that Hermite polynomials are either odd or even. All right, maybe we can do that. So we're now going to integrate from minus infinity to plus infinity. We have these constants. These constants, as we know, that's an even function, so we have even. And no complex conjugate, but the Hermite polynomials don't have I in them, so the complex conjugate of Hermite polynomial is just the Hermite polynomial. H2 is n equal 2. That's an even function. That's an even function. Let's look at this, x squared. Well, if you replace x with minus x, you're going to get the same thing. So that's also an even function. Let's look at x. X is an odd function because if you replace x with minus x, you get minus that function. So this is an odd. And similarly, these constants here are even. H2 is even. And the exponential is even. So we have even, 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 even. There's one odd one in here. So if you just even times even will give you an even function. And even times an odd will give you an odd times an even will give you an odd, and an odd times an odd will give you an even. Well, just maybe let's write that over here. Even times even is even. And odd times an even is odd. And even times an odd is an odd. And an odd times an odd is an even. So we multiply all that together. This is the integral from minus infinity to infinity of an odd function integrated over some region of space. I claim that the integral over all space of an odd function, this is equal to 0. So the expectation value for the harmonic oscillator in the n equal 2 state, the expectation value of position is just 0. Now, let's talk about why this is odd. Well, let's write an odd function. So an easy odd function will be f of x is equal to x. So here we go. F of x is equal to x. And this is an odd function. Now remember, integration, when we integrate, and we're just, this is x and this is f of x, we're going to integrate over all space minus infinity to infinity of this odd function. Integration is essentially a summation. So we're summing this value and this value and this value, but for every positive value we have a corresponding negative value. Here's a negative value, there's a positive value. So as we sum up, or in other words, as we integrate across here, for everything positive we'll have an equal negative, it all add up to 0, so that'll be equal to 0. So that's why integration over all space of an odd function will be 0. Now, so we're saying, so for the Hermite polynomial n equal 2, we expect the expectation value to be 0. In other words, the position of the particle should be right in the middle. All right, so let's see if that makes sense. Let's go to a spreadsheet that we looked at various probability density functions. Oh yeah, so here's a probability, so it's symmetric, and so you would expect that on the average it would be right there, x equals 0. All right, let's look at the n equal 1. Yeah, so we have a probability lobe over here and here. They're equal, so on the average it would be right in the middle. And here it is for the n equal 2. Yeah, we expect, again, we have probability being here, probability being here. On the average, you expect to be right in the middle. So that's what we expect. And the expectation value, we expect to be 0 for any Hermite or any harmonic oscillator. That sort of makes sense. I mean, duh. We have, here's say the molecules vibrating, and we have a center of mass, and just vibrating back and forth here, but you expect that on the average it'd be right in the middle as it oscillates. Another way to look at that, a third way to look at that, I should shut up pretty soon, is if you look at the potential for a harmonic oscillator, the potential, on the average you expect it to be right in the middle because the potential is symmetric. All right.